Like I need a microphone. Can you hear me?
Yes. John, can you put that on full screen?
Yeah.
It's a great pleasure to introduce John Dowling of Louisiana State University, who's going to talk to us today about inefficiency of classically simulating LOQC with Fock-state input. Thank you, John.
So as the Mayor McCheese, as Mike referred to me in his previous talk, I'm happy to be here, and thank you to the organizers who escaped before I actually started talking. Thanks, Barry. And the Chinese organizers. Well, this is my name in Chinese characters, John Dowling, and it's very means spiritual alliance with this particular set of characters. So most of the talk is sort of wound up in several papers, introductory papers on boson sampling, the inefficiency of classically simulating linear optical quantum computing devices in that context. So they're listed there. And my editor says I have to always shamelessly plug my book at every opportunity, so consider it shamelessly plugged. People found, that was my sister actually wrote that, so but in any case, that's the book plug. So I'm going to talk about sort of how I came to boson sampling through walking through the wilderness in a direction that was completely orthogonal to what most people who were doing boson sampling were doing at the time. And in fact, the first time I heard about boson sampling was in a talk by Andrew White. It was in 2012 in NASA Ames Research Center. Unfortunately, my talk was right after Andrew's, and I was fiddling with my slides, and I wasn't paying too much attention. But I went back and looked at my notebook. And in the notebook, I write down the name of each speaker and I make some comments. The only thing I wrote next to Andrew's name was Andrew White is experimenting with permanence. So, and I drew something that looked like this. You know, so this is a hair curling machine from the 1930s, and in the US we call this a permanent. It's that's what I thought Andrew was working on, and I paid no attention. Probably I should have paid more attention to the topic. All right, so. We came at this actually from looking at Alberto Bruzzo's paper with Jeremy O'Brien, and I'll get to that in a second. So first up, I'm going to start off with why I thought personally that linear optics sucked for doing anything interesting computationally, quantum computing wise. And when I say linear optics, I mean passive linear optics without the feed forward or the projected measurements that makes linear optical quantum computing work. So this is a funny paper by this guy named Cherney that came out, this is pre-Shor, 1993, where he said, oh, you can actually make a linear optical interferometer with a bunch of slits, and you'd make a traveling salesman problem solver. And it was, it would actually give you an exponential speed up in time, but it blows up in energy, okay, so which is an interesting thing. So you think maybe you got an advantage, but it doesn't work. And then these two knuckleheads, John Clowes and Jonathan Dowling, got together. And for a while, we thought we had some sort of all-classical factoring algorithm with only linear optics. And that also turned out not to be true. This was a Talbot interferometer. And you can show you can use Gauss sums. That Wolfgang Schleich has made a cottage industry of this now. In Talbot interferometry to factor numbers, but there's a blow-up in how long it takes. Okay. And then there's this old paper by Adami, Kuyat, and Cerf, where they actually had a scheme, single rail, all linear optical quantum computing. They showed it was universal, but the problem is the interferometer blows up in size. Okay, so after you see a number of these papers and write some yourself, you begin to think linear optics is good for nothing. You have to do something with feed forward or so forth. So, and then this paper basically says we have a bunch of squeezers and so forth. Squeeze-like with passive, squeeze-like sources with passive linear optical devices in the middle. You can't do anything with that either. Now we all know linear optical quantum computing, KLM-wise, is a road to QC, but that's because John Sipe and I proved in 2002 that there's a hidden curve on linearity when you do the projective measurements on the ancilla. So in some sense, linear optical quantum computing has an effective hidden nonlinearity in it, and away you go. Okay, so linear optics is useless for anything computational wise. So this, then my road to boson sampling followed two of my undergraduate students, and we went, where's Alberto? Raise your hand, Alberto. Ah, you're right in the front. Ah. We you read your nice paper, and where they did quantum random walks with single photons, as Dirk England mentioned yesterday, is perfectly classically simulatable with Maxwell's equations. You really need two at least to see something interesting. So they did a nice experiment with two random walk photons in an interferometer, not quite this setup. And I said to the undergraduate students, well, let's generalize this to arbitrary number of photons, and we'll write down expressions for all of the possible coincidence counts, the probability that D1 fires, and D3 fires, and D5 fires, and put it in closed form, or write this up and submit it to Optics Communications or something. It'll be a nice honors thesis project for you two guys. And so we made this little Galton board kind of interferometer with beam splitters, N photons in here and M photons in here. And the issue was they kept coming back to my office and saying, John, we can do like 3 or 4 photons and maybe 6 levels before the computer code gives out. And I'm having no luck with the analytic. One was doing the analytic part, the other was doing the numerical part. And they said everything blows up, it's all exponential. And I said, now, Brian and Robert, that's silly. This is linear optics with non-interacting photons. Nothing complex is going on. I know you're undergraduates. Whenever you see a hard-looking equation, you think something exponential is happening. And go back and relook at this again. Okay, and so I didn't know it was supposed to be computationally difficult because of all of these previous papers, right? So what was going on? So finally, I said, look, I will show you there's nothing complicated going on here. I rolled up my own sleeves, began writing on the whiteboard, and then, of course, disproved my own conjecture. So, and the undergraduates were right. So there's something funny going on with this system. So the issue is that you start getting multiple applications of Hongo-Mandel effects. This is a Hongo, we call this generalized Hongo-Mandel effect. You send it a 2-2 Fock-state. You get a noon state-like piece and a little poop state thing in the middle. And the issue is that the number of terms that look like this, so if we think of each one of these terms as a basis vector for a Hilbert space that spans a number path entangled space, that the number of terms grows exponentially. So they were doing it 2 ways. One was doing the Schrodinger approach, Schrodinger picture, and one was doing the Heisenberg approach. And I think the issue is that I forgot about my own paper with John Sipe, that I think it's a misnomer, I'm looking at Andrew White now, when people put non-interacting bosons in these papers.
Agreed. Okay,
we're agreed. A lot of these papers, particularly some of the early theory papers, it's non-interacting bosons. Well, they're not non-interacting, they're doing something like this via the Hongo-Mandel effect. There is an interaction via a bosonic overlap interval. There's not actually an interaction term in the Hamiltonian, but they are overlapping. I can shut the doors, but I'll just be louder than them. Okay, very good. And so they are interacting via the Hongo-Mandel effect, okay? And that interaction, followed by projected measurements, whether they're done in the middle of the calculation or at the end, gives rise to an effective nonlinearity. So we think there's actually a hidden pure nonlinearity in boson sampling. We haven't worked it out yet, but that's one of our research projects. So this is what people in StatNet mean by non-interacting bosons. There's a boson here, a boson here. You can get a double occupancy at the center point here, but then they just go their merry way and they don't do anything. Okay, that's a non-interacting boson. That's not what we have in photonics. The photons talk to each other. The overlap gives rise to the sticking of the bosons, and both go this way, both go that way. And we all know the Hongo-Mandel effect. So this is non-interacting bosons. That's not what we got. Okay, they interact. So this is Brian, poor Brian. His job was to do the Schrodinger picture. So the idea was that you take your photons, start with 1, okay, and chase all of the possible paths. We call them Feynman-like paths through the interferometer. Assign amplitudes to them, add them up and square them, and you can calculate the probability a given detector would fire, okay? And so you can see here's with 1 photon with this particular, we actually use real experimentalist beam splitters, not Hadamard's and so forth. So that's why it's not symmetric around the center. It doesn't fire here. There's a high probability of this one firing. Then you can do the 2 photons. And again, you have all of these paths. You tabulate the paths, add them up, square them, and then you can get you can calculate the probability a single detector fires, a pair of detectors fire in coincidence, and away you go. And Brian comes back and starts complaining, but I can only go to like 3 or 4, and then it gives out. And I'm like, look, okay, here, let's do 3. I like this picture. This is an exploded Rubik's Cube. It's a generalized 3-photon Mandel effect. And these white boxes in the center of the cube are places where no photons ever go. The photon probability actually cancels out. And the reds are high probability. Okay, so that's about as far as they could go. And I said, well, look, let's analyze your mythical claims of exponential growth. And so again, as you go through these, it takes 8 paths to compute all of the possible potential outcomes with our Galton board for the number of levels I just showed, okay? Rapidly goes to Helena Handbasket, old girlfriend of mine. So how many paths? Let us count the ways. So we start with n photons here, m photons here. These are beam splitters. We have tunable possible phase shifters. We're doing the Schrodinger picture, so we write down the Schrodinger wave function amplitudes at each level. L is the number of levels in the interferometer, so it's a resource counting thing, so we begin to tabulate. N plus m is the number of photons in the input, and you can count the number of paths quite easily using some combinatorics, and the number of paths is 2 times L n plus m. So just to give you an example, if you have 9 photons, it's 16 levels deep. There are 5 times 10 to the 86 total possible paths that poor Brian has to add up by hand in order to get the answer that I would like for just this machine, which is 4 orders of magnitude larger than the number of atoms in the observable universe. So much for the Schrodinger picture. Okay, but we know that the Heisenberg picture is always, almost always, when you're doing linear optical or any interferometric calculation, Heisenberg picture is always quicker. It may be less insightful, but it gives you the answer faster. You can calculate quicker in Heisenberg. So I got turned from Brian to Robert. I go, how's Heisenberg looking? Not so good. Okay. So I'll take a little respite here. At some point, we wrote up the 3-photon result without the general result, which we were still agonizing over. And we mentioned this business about the apparent exponential growth, and we shipped it off to the, I think it was Josephine. And the referee was mostly positive and said, this was 2010-ish. He wrote back and said, in the second or third round, he said, can this be connected to Scott Aaronson's boson sampling? And my response was immediate and quick. What the heck is Scott Aaronson's boson sampling? And the referee kindly provided us with this reference to a 94-page paper that read a lot like this, okay? And I thought, well, I don't have time to read a 94-page paper. I'll just jump to the primary conclusion, which is this, something about the polynomial hierarchy collapsing, and we have acronyms raised to the power of acronyms contained within or possibly equal to acronyms raised to the power of other acronyms or raised to other acronyms. So that NASA has nothing on these guys, right? I mean, the acronyms grow as powers. If NASA finds out that this is the way to generate new acronyms, we're all dead. And so there was some discussion about this back and forth on my blog, on Quantum Pundit, and Scott Aronson's blog, Shuttle Optimized, about permanence and determinants. And I said to myself, this I know from nothing. Borjamoy. I'm not going to figure out what's in this paper, which is what Scott Aaronson insisted I had to do before I could talk to him. So I feel like we were 2 detectives. So I've got this guy here, Aaronson, and then there's Colombo down here who's Dowling, and this guy only speaks French, and he, through hand motions and so forth, I understand that he thinks there's a dead body buried under a bush. But in order to understand his theory about the dead body under the bush, I need to either understand French, but my approach is to get a shovel out of the boot of my car and begin digging under the bush. So that's what we did. All right, back to the Heisenberg picture. So in the Heisenberg picture, we'll take m equals 0, n is not equal to 0 in the interferometer here. Okay, this is m and n input. You can write down the first few terms and then generalize this by induction. And write down a general formula for the state at any level in terms of the operator's A dagger on the vacuum. And it looks like this. And so you can, in closed form, these are not coherent states. This is just alpha is a complex number. And so this is called a multinomial expansion. It's a combinatoric thing. You can look it up on Wikipedia or wherever you want. And then you can say, well, okay. So the idea then is that however many of these operators operating on the vacuum I have, each one of these terms operating on that vacuum gives you a different basis ket for a Hilbert space and the number of path degrees of freedom. So I can calculate how many basis kets I have and give you the dimension of the Hilbert space. And so there it is. The dimension of the Hilbert space is the binomial coefficient n plus 2l minus 1 over n. And so you can pick the computationally complex regime where n is approximately equal to L. And you work this out using Stirling's formula, and you end up with this number, which turns out to be much less than the Schrodinger picture number, but it's still exponential, so it still sucks. So taking L equals 69, number of photons is 137, the dimension of the Hilbert space is 10 to the 81. Again, the number of atoms in the observable universe. The Schrodinger picture, the number of paths is 10 to the 2,845. So Schrodinger picture sucks royally, but still the Heisenberg picture also sucks. So this implies that the Heisenberg and Schrodinger pictures, although mathematically equivalent, are not computationally equivalent. There's a different computation involved in terms of resources doing Schrodinger. This proves that Schrodinger is harder, actually, but the Heisenberg is not simple enough to allow us to get an answer. We put that in the paper, and the referee wrote, "This result is implicit in the Gottesman-Ganil theorem." And I'm like, who knew, right? Okay, great, okay. So, in any case, you can put in coherent states or squeeze states, and nothing like this happens. So this is my rendition of the polynomial hierarchy collapse. And these are actually dominoes. It's collapsing at a 10th somewhere. So we sent this back, the new paper with this analysis of the exponential blow-up. We sent it to PRA. Referee A says classical computers cannot officially blah, 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 unless the polynomial hierarchy collapses. I have to go back and read Aaronson's paper. I don't want to read Aaronson's paper. It's 94 pages long, and I don't understand anything in it. Okay. Referee, we responded to them saying very few physicists know what the polynomial hierarchy is, and Physical Review A is not a computer science journal. Thank you very much. Referee B actually had a brain and was much nicer to us and said a very physical and accessible approach. And that's what we're trying to do. Take this thing, wrench it out of the hands of the computer scientists at MIT, no offense, Dirk, and convert it into physics and then regurgitate it to the physics community in a form that would be digestible, like a mother bird. Okay, so if we could actually get this, we need to bolster our argument, and this goes back to the determinants versus the permanents. And I was puzzled over the determinants versus the permanents. And I knew permanents were hard to calculate. I knew determinants were somewhat easy to calculate, but I was hung up on the dimensionality of the Hilbert space. Because when you go back to the Feynman lectures on quantum computing, the Feynman papers on quantum computing, he focuses on the fact that when you entangle qubits together, that blow up in the Hilbert space is the thing that causes you to be unable to simulate it on a classical machine. However, we know from the Gottesman-Ganil theorem that you can have an exponentially large Hilbert space using only Clifford algebra operations and still simulate it efficiently, so there are exceptions to that rule. Sometimes there are shortcuts through the Hilbert space. So here are the bosons. Okay, this is sort of a hybrid notations, two spin-up bosons. They interact. This is the Hong-Mandel, and they come out spin up here. And you can send in bosons in a singlet state into a regular interferometer. And this theory of beam splitters for bosons and fermions was something worked up by Rodney Loudon in the mid-90s. So if you send in a singlet state like this, you actually get a Pauli exclusion-like effect. You get an anti-Hong-Mandel effect for bosons if you set it up like this. And the reverse happens for fermions. And this is where I was hung up. The exponential growth comes from multiple applications of the Hong-Mandel effect. And I didn't think there was a Hong-Mandel effect for fermions. So I thought there would be no blow up in the Hilbert space. I was wrong. I'm always happy to be wrong. When I make a conjecture, if I'm right, I'm happy because it means I know everything. If I'm wrong, I'm also happy. It means I need to learn stuff and I don't need to retire yet. So I was wrong. So this is what I was thinking. Pauli exclusion says you take these two guys in, these two guys go out, no Hong-Mandel, no exponentially large Hilbert space. However, if you send them in like this, an anti-symmetrized fermion state, they come out like this. Okay, there's spin, and we don't violate Pauli because they're anti-aligned. But this is the fermionic Hong-Mandel, 2, 0, 0, 2. And so there is a Hong-Mandel effect for fermions. And so multiple applications of the Hong-Mandel effect for fermions gives you a blow up in the Hilbert space. Not quite as bad as with bosons, but still it's exponentially large. And you would think it would be impossible to simulate what's going on with the fermions as well. And this is an interesting thing when you teach elementary quantum mechanics. this business here explains the bound state of neutral hydrogen molecule, because a neutral hydrogen molecule, it's antisymmetric in the spins, which means it's symmetric in the spatial wave function, which means the overlap is a bosonic attraction, so it sticks. And so this is how you explain neutral hydrogen to the sophomores. All right, so now there's a Hahn-Mandel effect for fermions. You also can calculate the dimension of that Hilbert space. The fermionic one still is 2 to the 2n. It blows up. And so you would think you couldn't computationally do anything with this. But the point is, in order to figure out what's going on here, you have to properly symmetrize your wave functions. And for bosons, they have to be properly, totally symmetric under label interchange. The fermions need to be antisymmetric. Everybody knows about fermions with the Slater determinant. That's an automatic system that allows you to find the most general input state or the most general output state. They can be connected in an interferometer by matrix transfer, which is efficient. So the point is, for the fermions, the most general output state needs to be something that looks like a Slater determinant, and you can compute that because magically the determinant has a fast algorithm. It actually goes like n squared, not n cubed, the fastest algorithm. We can dicker over that over here, but I think it's n squared. And you do row reduction or Gaussian elimination, get it in diagonal form, and then take the product of the diagonal, and that gives you the determinant. That's a very efficient process. There is no such thing for permanence. That's the problem. Okay, so when you do this with bosons, basically there's a connection between the inputs and the outputs. So if you have to calculate the most general input state, which take the unitary U dagger, that's the most general output state, you have to fully symmetrize it. The analog of the Slater determinant would be, for the bosons, the Slater permanent. Now, Slater never wrote down a permanent, but the idea is that you would have a permanent of a matrix that would automatically allow you to calculate the most, the general symmetric state under particle interchange. And that's the problem. So, totally antisymmetric fermions, determinants, totally symmetric bosons, and away you go. So Slater permanent, Slater determinant, remind you what the permanent is, but we've already heard this. The permanent, by the Laplace decomposition, every school child knows the determinant. It's plus, minus, and then you take the subdeterminants. It's 2L factorial steps if you do it this way. This is also 2L factorial steps. This is the permanent where they're all plus signs. When I gave this talk in Rochester a year or so ago, Kimball came up to me at lunch and said, you know, I never heard of a permanent before. And I said, did you see Andrew White's new hairdo? And in any case, so the point is, the fermions, you can calculate the determinant. The most efficient algorithm, row reduction, gives you L squared number of steps. The most efficient algorithm for calculating the permanent, to find the symmetric wave function, is the riser algorithm. It goes 2 to the 2L times L squared. That 2 to the 2L kills you. You cannot give it a set of input states, calculate the most general output state, because in order to do this, I need to compute the Slater permanent, and I can't do it on any reasonable machine. And that's the difference. And so I learned it's not just the Hilbert space. For the determinant, just like the Clifford algebra shortcut, there is a blow up in the Hilbert space, but there's a shortcut in simulating it because the determinant is easy via the Gottesman-Canel theorem. No such shortcut here. Fiber. And so here is a sampling of publications in bosons, sampling 213 to 214. I haven't updated it yet, but I'm sure it goes on forever. So many of the people are in this room. Now that I understood what was going on and I was up to speed, I still didn't want to read Scott Aaronson's paper. We began writing physics articles on boson sampling that were meant for physicists, not computer scientists. So we don't have acronyms raised to the power of acronyms, raised to the power of acronyms contained within other acronyms raised to the power of acronyms, and so forth on sampling for physicists on the archive, soon to be published. We just heard from Mike Steele the joys of multiplexing. The point is that the question is asymptotics. Does this work if you scale this up to arbitrarily large size? For boson sampling, depending on the efficiency of the SBDCs. As we know, the SBDCs is sort of like the Dirac's favorite joke. I can tell this with Barry in the bathroom. It's told to me by Baruch, my thesis advisor. So the Irish priest is invited to the family's home in Ireland, and introduced to the children, and the mother introduces to 10 children in the Irish family home. I'm Irish, I can tell these jokes. And there are 5 identical sets of twins. And the priest is astonished and says, do you mean to say you always had twins? And the wife, she gets embarrassed and says, oh, Father, no, most of the time we had nothing at all. So that's SPDC. Most of the time we have nothing at all, but every once in a while you get a pair of twins. You know, you got it. Okay, great. That was Dirac's favorite joke. Okay, so most of the time you get nothing at all, but when you do, you multiplex it, store it, and then you could, given certain efficiencies of SPDC, the detectors, you can actually show this is scalable to arbitrary ends, not just. This is Dirk's talk from yesterday. It motivated some of the stuff he was looking at, that you can change the spatial interferometer into a temporal interferometer and do boson sampling that way. And we cooked up the scheme for doing general unitaries in the R class that allow you to do boson sampling in time. There might be an advantage in doing that. And Keith Mote's alias, the beer thief, is sitting there in the front row looking for a job in about 6 months. Apparently not in Shanghai anymore, but someplace maybe where there's less beer, like Berlin. But there's been a nice collaborating with Alexei Gilchrist and Peter Rodi at Macquarie University that's ongoing. Evidence for, so one of the things we did is I said, okay, I'm tired of this boson sampling with 1s and 0 photons. Let's check every possible quantum state of light that we have ever heard of and see if it can be used for boson sampling. And I know every single quantum state of light I've ever heard of. Okay, so one of them is the cat state. So we replace the single photons going in here with generalized superposition of coherent states, which are cat states. And we show in the limit that the cat states are very small. You essentially get, if they're odd cats, you get zeros. If they're even cats, you get ones. In that small limit, you can actually recover Aaronson's boson sampling because you're really treating the coherent part as noise. Not too sexy. This one's a little bit more interesting. These are photon-added coherent states, which have negative Wigner function. And again, if the coherent part is small, it rolls over into Aaronson's boson sampling because essentially the single photon part dominates. If the coherent part is large, then it can be simulated classically. So there's some funny transition from boson sampling inefficient to coherent state efficient to sample that we don't understand yet. Some kind of phase transition between computationally complex and computationally not complex. This one is new, so this one is quite cute. So what we've done is this is photon added or subtracted squeeze states. They look a lot like this, except they're sort of banana-shaped on the top, but they have a negative Wigner function. So this is regular boson sampling. You send in 1s and 0s, okay, and you do number resolved detection in the output. Here, we're sending in photon added or subtracted squeeze states. Some people know how to make these in the lab now by heralded, but still. And so here are a bunch of photon added squeeze states here, regular squeeze states here. Instead of sampling on photon number, we do parity measurement, and we sample on whether it's +1 or -1, even or odd. And for this, it is not just some kind of limiting case of the Aaronson boson sampling. It's totally new. It actually works for arbitrary squeezing parameter or the intensity of the squeeze state. So by switching from photon number to parity, we can do arbitrary squeezing parameter sampling. So this is a completely new set of states for boson sampling that does not just simply reduce in some limit to Aaronson's. Now, photons are our friends here, but people have already looked at using ions, where you replace the photons with phonons for boson sampling. This gets around the detection problem in many cases because you can detect phonons in ion traps to get all sorts of tricks. This is a scheme that we're looking at with Rice University. There's a guy by the name of Caden Hazard there who assures me that they can make optical lattices now to implement any arbitrary unitary. And the idea for boson sampling is you have a Haar class unitary down here. You put your atoms into an optical lattice in a BEC, make a Mach transition. Randomly, you'll get 0 or 1 atom in the optical lattice sites. And you can tune it so it's 50% zeros and 50% ones. From scattershot boson sampling, we don't need to know which ones are the zeros and ones in advance, as long as we characterize it after they're made. We drop them through this is my unitary linear optical device is replaced with an optical lattice. We count the atoms that arrive here, and the efficiency is 99.99999% because we don't lose the atoms. And you get the boson sampling that way. And what's my time? Who's keeping time?
You've got 12 minutes.
Oh, well, I'm almost done. I'm going to get a drink of water. So, one problem with boson sampling is that it's not known to be good for anything useful. So, to me, the situation is like quantum computing circa 1998 or 1999, where Richard Jozsa and David Deutsch proposed the Deutsch-Jozsa algorithm, which is provably gives an exponential speedup over a classical machine on determining whether a function is balanced or unbalanced. Now, that's very nice, and except nobody really cares at all if a function is balanced or unbalanced. Now, we might want to know if Andrew White is balanced or unbalanced. I don't care about that greatly, but sorry, Andrew, I was happy that you showed up just in time for all the insults. So.
I'm thrilled as well.
But it was not a problem anybody was interested in. And it's the same with boson sampling. There's no known practical application of boson sampling other than it's an example of something that's hard to do on a classical machine that's easy to do with linear optics. So I actually submitted a couple of proposals to NSF and the Army Research Office making the following claim, that we're producing huge amounts of number path entanglement inside of the interferometer for free without doing anything. Nuance states require some heralding, some Kerr nonlinearity, something to make it that way. And so they're resource intensive. But here I'm not really doing anything. Once I get my single photon sources that everybody in the world is trying to make better and better, I just launch them into the interferometer, and the natural repeated application of the Hongo-Mandel effect going through the interferometer generates this exponentially large number path entanglement. From nuance states and all the way back to the 86 paper of Yerke, on the Yerke state, we know number path entanglement is a resource for quantum metrology. It seems natural to ask, is the number path entanglement generated naturally by the linear evolution of the photons in the apparatus useful for metrology? In other words, we take these phase shifters here and make them unknown phase shifters that we're trying to measure. And the answer is yes. Okay, and Keith, the beer thief, will be talking about this Saturday, tomorrow. I think he has a 45-minute talk on this. But so I'll just introduce this. He'll go through it in gory detail. And so the authors are Motz, Olson, Rabot, Dowling, Olson, and Rode or Mordor. All of this stuff here is an ordinal resource counting, or ORC, that we use to justify our resources. We have a quantum Fourier transform. You can take the quantum Fourier transform and recomposition it into a linear optical device. We send in all ones. We have our unknown phase shifters here. There's a linear bank of them, but we explain how you can do that using, for example, optical magnetometry. These are control phase shifters. In all of optical metrology, you always have to tune the unknown's phase to a sweet spot via control loop. And so that's what the thetas are doing. This is the inverse quantum Fourier transform. Again, decomposition that up. If the phase shifters are turned off, that's a deadity, and so we get all ones out. So we tune it to we're most likely to get all ones out, and then that's our signal, okay? And we do a sampling on that, just a la boson sampling. And we do a signal-to-noise analysis with error propagation. It's tricky because we have to calculate the permanent of the big-ass matrix. For reasons that we do not understand, the QFT seems to have a closed analytical form, so it's probably not in the sharp P hard class. It's probably in P, but we don't have a proof. But we're able to get a closed form solution, check it against Keith's calculation using the Reiser algorithm, up to about 20 or 25, which is as much as Andrew White or anybody else in this room is going to, or Philip Walther is going to do in the lab anytime soon, 25 photons. So we don't have a proof for arbitrarily high end, but we have a conjecture. And so the black line here is shot noise. The orange line here is Heisenberg limit, and the red dotted line is this. So it lies just barely above the Heisenberg limit. So the takeaway point is, without any fancy noon state preparation or multiple passes or anything else, you take single photons and launch them into a passive optical interferometer, and you nearly hit the Heisenberg limit without doing any work. We think that's a big deal. It just appeared at PRL last week. And Keith is going to go through this in gory detail, and he has all sorts of cartoons with forks and glowing eyeballs and stuff to make this interesting. So what's the moral of this story? When I gave this talk, again, it was in Rochester years ago. Daniel James also gave a talk on boson sampling. He made a comment that I really liked. Quantum physics is not a branch of computer science. Right? So it was really goading to me I worked on the theory of linear optical interferometers with quantum states of light for 30 years, okay? And then this upstart from MIT computer science department named Scott Aaronson comes along and says, oh, you optics boy, you have missed something completely deep about linear optical interferometers that only we at MIT understand. And in order to understand what we're doing, you have to read this 94-page paper and decode everything in it. And so I said, damn if I'm going to do that. So what we've done is cooked it back up again in terms of physics language, so people in this room don't have to read the 94-page paper and understand everything. And along the way, I learned a little bit of computational complexity that kicking and screaming I try to avoid. But that's the whole point of quantum computing, right? The physics tells you what you can compute, not the computer science department. That's it. That's our group. Come join us. Thank you very much. You have heart palpitating.
Clapping one-handed. Questions? Yes, Ish.
Thanks for the nice talk, John.
Ish! Thanks for helping organize everything. You've done wonderful.
My pleasure. Could I have a look at the Rubik's Cube again? That was a really nice figure.
Which one now?
The Hongo-Mandel Rubik's Cube.
Ah.
And
That would require this thing to actually function. I can say in the paper. Okay, so there was a Rubik's Cube with the different colors. Imagine it was up there now.
Yeah, okay. While it's turning on, I have another question.
Ah,
Oh, okay.
would you just hold that? And I mean that. And there's a disadvantage. There, that.
What are the axes on this plot?
Ah, coincidence counts. So, sorry, they're unlabeled. So this is detector 1, 2, 3, 4, 5, 6. This is detector 1, 2, 3, 4, 5, 6. So this is the probability that detector 3 gets 3 photons, because it's a 3 in from there, 3 from the top, and no, it's 4 in from there. Is it 1, 2, 3, 4? Right, so this is detector 3, 3, and 4 all fire in coincidence, and it doesn't happen.
Okay. Yeah, that's a nice plot. The other question I had was about boson sampling using non-classical states of light. It seems to me that some kind of non-classical behavior is required, but do you have a feeling of how much non-classicality and
Right, so this is the paper with the photon added coherent states. We like that. And so we have a feeling, but we don't have any proofs. There's a, I can, yeah. There. So we also have the same idea that somehow the negativity of the Wigner function was required. That was a conjecture of mine that was disproved by Tim Ralph and his gang, where they showed you could do boson sampling with all Gaussian states. Okay? But it was kind of a cheat, because half of the Gaussian states are actually are being used to herald at the end as opposed to the front. So modulo that paper, we suspected something to do with the negativity of the Wigner function. And in fact, this thing here, this photon added thing, as the coherent component gets larger and larger, it goes over to coherent state. Coherent states, we have a simple proof that it's easy to simulate. we had, when the coherent state component is small and it looks like this, it's not easy to simulate. We don't understand the threshold or the phase transition. So I suspect it's something to do with the negativity of the Wigner function modulo the sort of fake Gaussian sampling that Tim Ralph did. Don't tell him I said that. It was very nice, but it's...
It's all right, I told him that as well.
Okay, yeah, it's fishy. Yeah, okay. So we're thinking about this. One of the students, in fact, is looking at this exact problem and trying to do I would call it a phase transition analysis to see if there's a type 1 or type 2 phase transition.
How about you?
So in the metrology paper, which I have only...
You should ask Keith on Saturday.
Well, maybe I'll ask you first, so we can think about it.
Yeah, okay.
So how do you select this sequence after the Fourier the quantum, the QFT? You have this sequence of phases.
Right, so
how do you select that function?
There's an old saying that people like sausages, but they don't really like to hear how they're made. Okay, so it was Peter Rode who conjectured that the QFT would be a good unitary to try because it kind of gives you a democratic phase sample.
Yeah, it mixes well.
Right. If you put just a bank of phase shifts phi at every one, it commutes to the outside and you get no signal. That doesn't work. So we just tried everything. Okay.
Sorry, say again this thing?
If you just put all phi's here,
okay, yeah,
it commutes through and you get no signal.
Yeah.
That's bad. If you put one phi in the middle, it sucks. Okay. And then I said, why don't we just try a linear gradient of phi's? And I was thinking like a gradiometer for gravity gradiometry. You know, you want to know the gradient of the signal, not the signal itself. And then, and that worked really nice. That's the red curve here. And then we cooked up a story. We said, okay, imagine you have an unknown magnetic field, okay, and you're trying to measure that. So the signal phi is proportional to the unknown magnetic field uniform across the chip. But it's proportional, so I have an EIT median in here. Okay, so the signal phi is proportional to the magnetic field times the length. So I make this 1 micron, I make this 2 microns, I make this 3 microns, and so I can actually put the gradient into the chip in terms of the magnetic field sensor. So we would build it into the device, the gradient.
But there might be other functions that you pick that work better.
Indeed. It turns out, just by accident, the linear function allows us to compute the permanent. When you put a square, Lord knows, the simple pattern breaks down, and so it might be, but we haven't checked it numerically, and it's difficult to do because the permanent filter becomes hard again.
Thank you.
All right, we have 2 more questions. Philip?
Hi, so thanks for this very nice talk.
You're supposed to do this experiment.
Yeah, but it's nice to see it from using physical approaches, not the
Alan
science.
Asper-Guzik said, this is a nice paper. Either Andrew White or Philip Walther or Jeremy O'Brien should do the experiment. So I'm taking bets.
Okay.
But I have one question regarding the metrology application. So it seems you really reached the Heisenberg limit, which is normally done by Noon states. And if you compare to Noon states, they're very sensitive to loss. So here I'm surprised that you can achieve similar precision or resolution by using this boson sampling approach. My question is, how does loss show up here? What happens if a photon gets lost in that?
So they don't give out prizes for people who publish best. They give out prizes for people who published first. So as soon as we got a result with no loss and no dephasing or anything else, we published it. So Andrew asked the same question earlier in the week. So in the paper it says, at least for now, we're hoping that this device is good enough, either the ones they make in MIT or in Australia, that the loss level is low. We tune it so the phase shift bank is close to 0. The most likely outcome is 1, 1, 1, 1, 1, 1. Our signal is any drift away from that. So if we don't count all ones coming out, and if 10 photons come in, we don't count 10 here, we throw that out. We don't bin that into our data. And if we don't throw out too many of those, there's still an advantage. The question is, as a function of loss, where's the threshold? We're calculating that now. But to turn your question politically in a different direction, one of the referees said, how does it respond to dephasing? Noon states are even worse to dephasing because it goes like e to the n squared, okay? in terms of dephasing. So we did a dephasing model here. We put in random oscillating phases in each arm, and we compared it to the noon state, and actually this thing, it seems to be almost immune to dephasing compared to the noon state. The noon state, as n goes high, immediately goes way above Heisenberg, even the shot noise limit, where this thing, you can't barely even see it. So somehow this is immune to dephasing, which I suspected it wouldn't be, knowing what noon states are, and it was a surprise. And then the guy said, oh, that's great, publish in BRL. Okay, so, but we haven't checked loss. It'll be some trade-off between how much loss there is and how many times we have to throw away events. And we don't know what that is yet.
Okay, thanks.
There's a lot of questions, but I think we've only really got time for one more. I'm sorry.
Well, the coffee break will be short because the coffee machine doesn't work.
No, it's working.
Oh, it's working! Oh, thank God!
People have gone out for coffee already. Vincenzo.
Thank you, John. Very
Now I
nice.
can die happy.
I have a question. First question is about this metrology scheme. Do you need to have this linear dependence in the phase? How much precise needs to be the linearity dependence to have this work?
So this probably harkens back to the dephasing, right? So we put, to check the dephasing, random fluctuating phase shifters in here, which made our linear grading less precise. And we took that dephasing up to 10% of the, if phi ranges from 0 to 2 pi, we went to 10% of 2 pi. That's how big the fluctuation could be. That was the half width. And we saw almost no effect.
Okay, so it doesn't need at that point to be perfectly linear. Maybe
It
that's
looks
the
like
other functions that maybe
yeah.
work out.
The other functions are difficult to calculate because you get Gauss sums, so you're going to need Wolfgang Schleich to help us out on this.
Yeah, I mean, we did a factoring actually algorithm with Gauss sums that after your work.
I think my point is this opens up,
But
the whole point is that this is actually useful for something unlike boson sampling.
okay.
Take it away.
Sorry, there are still questions. John will be available in question
I will
time.
be
Let's
guzzling
thank
coffee.
both the speakers for their fascinating talks
Yes.
this morning.
Where's Mike? Mayor McCheese, is that what you called him, right? Very good.